Okay, we're going to look at a new family of functions now, and I'm going to point out to you something here is that location is important. We've been studying functions that have terms that look like this, x to a power. Okay, we've been studying polynomials, we've been studying rational functions. In this scenario, the base is a variable and the exponent is constant. X squared being an example. In this function over here, those roles are reversed. Here, the base is constant, 2 in this case, while the variable is the exponent. So this would not have fit into our polynomial pieces. This could not be part of a polynomial. It's not x to a power, it's a number to the power of x. So this is called something different, and we call this an exponential function. Okay, so let's make a definition here. What is an exponential function? What does it look like? What are the restrictions? So an exponential function is any function that looks like a to the x. Okay, x is the exponent. That's where the variable is located. A is a constant. Now, are there restrictions on a? Yes. We want a to be a positive number because negative numbers create problems. For example, if you have a negative number to the half power, you have issues because that's really the square root of a negative, which we don't like to deal with in this course because we want to deal with real numbers. We also don't want a to be equal to 1 because 1 to any power is 1, and so that's kind of a trivial function. It's very boring. It's a constant function, so it doesn't really fit the exponential model we're going to see here. So a can be any number besides negatives. 0 can't be 1. Other than that, rock on. A to the x is an exponential function. So let's take a look at what the parent graph of an exponential function is going to look like. And we'll graph 2 to the x as an example. But we're going to see that all exponential functions follow the same basic shape and have the same basic properties. So this will be a good example for a parent function for this entire family. So let's do this by making a table of values, which is what we usually do when we don't know what a function's graph looks like. So let's plot 0, 1, and 2, and then we'll go negative and plot some of these values here to try and get a complete picture. So 2 to the 0 is 1, 2 to the first is 2, and 2 squared is 4. 2 to the negative first power. Okay, now we need to be careful and remember what this means. This means 1 over 2 to the first. So we're going to get 1/2 there, which means that this is going to be 1 over 2 to the second, or 1/4, and 2 to the negative 3 will be 1 over 2 to the third, positive 1/8. So now if we plot these dots, we're going to get a somewhat interesting picture here. We'll say negative 1 1/2 is here, negative 1/4 is here, and negative 1/8 is here. Okay, now I'm going to try and connect these dots as well as I can with a smooth curve. So some observations to make about this curve. This is going to continue and get larger as the exponent gets bigger. 2 to a big power is going to continue to get big. And then over here to the left, this is going to continue to get smaller, but we should notice that we'll never get 0 as an answer. 2 to no power will give me 0. And we'll never get below the x-axis either because 2 to a power has to be a positive number. So some key properties here that I think we need to note. Okay, an exponential function will always be positive, at least in the parent form, before you start doing transformations. An an exponential function is going to go through the point 0, 1. Because it doesn't matter what my base was, any number to the 0 power is going to be 1. The only exception being 0, but we know we're not going to counter 0 as a base. In this picture here, your exponential function is always increasing, getting larger as you go from left to right. And we should also see that towards the left, our y values get smaller and smaller, closer and closer and closer to the x-axis. So on one side of the number line, exponential functions have a horizontal asymptote. So horizontal asymptote of the x-axis, in this case, as x approaches negative infinity. No asymptote to the right, as the numbers will continue to get large as x gets large. Now, let's remember what we did in Chapter 2 with transformations. If we have the graph of f and we apply f of negative x, this is a transformation to the inside of the function, so it's a horizontal transformation, and the negative sign makes it a reflection. So this is going to be a horizontal reflection, which means it's a reflection across the y-axis. Hopefully that makes sense. And so if my original function was 2 to the x, then f of negative x would be 2 to the negative x. And so 2 to the negative x should look like a reflection across the y-axis of f of x equals 2 to the x. So what does that mean? We're still going to have the point 0, 1, but instead of increasing from left to right, I'm going to decrease from left to right, and my graph's going to level off towards 0 as x gets close to infinity. Okay? So take a look at this. I could rewrite 2 to the negative x as 2 to the negative 1 times x. I just factored the numerator, or not the numerator, I factored the exponent. And I could use the power to a power rule backwards and write that as 2 to the negative 1 to the x. And 2 to the negative 1 is 1/2. So I now have 1/2 to the x. That's an exponential function. And so I have now created a situation where you have not exponential growth, a function that increases from left to right. I have an exponential decay model, which decreases from left to right. So when does that occur? Okay, that's going to occur when your base is less than 1, and obviously still greater than 0. So if that's the case, then a to the x will be not exponential growth, but exponential decay. And we're going to see some situations where we're going to see where exponential decay can be useful in modeling things in the real world, as well as exponential growth. Features about this graph, you still go through the point 0, 1. That didn't change. Now your horizontal asymptote is still the x-axis, but it's at positive infinity rather than negative infinity. So horizontal asymptote of the x-axis as x approaches positive infinity. Your graph is still positive all the time, and your graph obviously is decreasing. That's why we say exponential decay. It gets smaller. Now, it's not necessary to write this stuff down. I'm going to go kind of fast through it, but a big application of exponential functions has to do with money, banking, and interest, which seems to pique the interest of students. So let's go through this real quick and just kind of show you how this pans out. So when you place your money in a bank, the bank pays you for letting them use your money. So they're holding onto your money and they invest it somewhere, and their hope is that they can make more money than they're going to have to pay you back while it sits there. Okay, the money they pay you is called interest, and it's usually based on how much you put in. Okay, so what you put in is like the base of the exponential function. Now, here's an example. Ally Bank offers 3.9% annual interest on a deposit of over $1,000. That was last year. I don't know if that's still the case. It's probably lower than that now. But how much money would you have in the bank after 1 year if you deposit $2,011.99? Okay, so the math to do that is pretty simple. You take your amount that you put in, $2,099, and you multiply it by this percentage, 3.9%, which is a decimal is 0.039, and that tells you how much money the bank's going to pay you. And if you just add that back to the original amount, that's how much you'll have in the bank. So you can see this calculation here. It says 2011.99 times 0.039 gives you $78.47 if you round up. That's how much the bank would pay you. And obviously you take that and you add it back to what you had initially. That's how much you have in the bank. Okay? So it says this gives us the amount of interest earned, which you add back to the principal, the initial deposit amount, to determine how much is in the bank. Okay, now, is there a shortcut to calculating how much is in the bank? And the answer is yes. Okay, in this case, you had your initial $2,011.99 and your interest, which was calculated by doing your initial amount, $2,011.99, times this interest rate, which was 0.039. And you'll notice that there's a common factor in this expression of $2,011.99. You can factor that out, and you have 1 plus this interest rate. So that would be a shortcut to figure out how much money you have in the bank after 1 year, is you just take your principal, multiply it by 1 plus the rate. Easy enough, but things get more interesting. Okay? A competing bank thinks they can do better with your money and is willing to try to entice you to invest your money with them rather than Ally Bank. This bank offers you a slightly smaller annual rate, okay, 3.88%, but it says we will pay you 2 times a year. They call that semi-annual compounding. So they're going to say, all right, we're going to take your money, and at half the year, we're going to pay you half the interest rate based on what you put in, and then we'll do the same thing at the end of the year. So that's going to happen twice. The question is it better for the investor or not? So what calculation gets done here is halfway through the year, you do the calculation. Principal, $2,011.99 times 1 plus, now my rate is 3.88% divided by 2. Divided by 2 because it's only been in for half the year. All right, so that's how much I have after 6 months. I'm not going to actually calculate that number, but let's just say that that's the number. Now, after 6 more months, the same thing happens. We multiply that amount, which is now in red down here, times 1 plus 0.0388 divided by 2. Whatever this comes out to be is how much money you have in the bank. All right? Now, this is where it gets even more interesting. Some banks do interest that way. Some banks do interest more often. They can do it monthly. 4 times a year, quarterly. You can do it weekly, daily, etc. And so, again, don't write this down, but I'm going to show you a table that shows you if you invest that $2,011.99, how much you would have in the bank after 1, 2, 3, and 4 years using these different compoundings. Okay? And by the way, over here is the formula for interest calculations. Here R is the interest rate written as a decimal, N is the number of compoundings, and T is the number of years. So you might have seen this formula before. Again, you don't have to write it down because we're not going to do a lot with this in class, but it's kind of interesting. Notice that, let's look at 4 years. At 4 years, if you compound your money once a year, you would have that much after 4 years, $2,344.70. And let's just say you did it every week, you'd have $2,351.53, which is a little bit more, not substantially more, but you can imagine that if your initial amount deposited was larger, then the difference would be larger, and it'd be kind of substantial. All right, you could also probably find a bank somewhere that would do your money, compound your money daily, every day, every hour, even every second. Okay, and in each case, you see that the amount that you have earned in interest goes up. So somebody somewhere said, hey, since if you increase the number of compoundings, you get more money, is there a limit to how fast or how often you can compound money for interest, and therefore is there a limit to how much interest you can earn? In other words, what happens as you let the number of compoundings, which is n, approach infinity? And this is kind of an interesting question. And I want to look at this real quick here, because this is going to give rise to something very special that pops up in mathematics quite a bit. and we'll see for the rest of the year. Okay, we have to do a little bit of algebra on this expression over here for accrued interest and money, amount of money in the bank. So we're going to make a little substitution here, and you'll see why in a second. So we're going to let M equal N divided by R. And let me come over here and notice that if N gets big, then so will M. R is fixed, okay? R is the interest rate. It's set at whatever it's set at. It doesn't matter in this case. We're going to see this is all independent of the interest rate, which is interesting. But if N gets big, so does M. Okay, so let's rewrite this expression now. We have your principal times 1 plus, now, if M equals N over R, then if I flip both sides, I'll get 1 over M equals R over N. So now I have R over N is going to be 1 over M. And what else do I have here? N, what would N be in this situation? N would be R times M. So this is now RMT up there as the exponent. And I'm going to use the power to a power rule in reverse and write this as 1 plus 1 over M to the M, and then I'm going to put the RT up here on the outside. Okay, convince yourself that that's legal because power to a power rule says I can just multiply the exponents, and I arrive back at my original expression here. So now we're going to focus on this inside expression. What does this expression do as M goes to infinity? So that's the question. As M goes to infinity, we want to know what does this expression here do? And let's go to Microsoft Excel to explore that a little bit. Okay, so here I have in Excel 2 columns. Here's my values for M, which are increasing powers of 10, because I want M to get big, get close to infinity, so I'm going to make it gradually bigger. And then in column B, we're going to calculate the value of that expression at these values of M. So recall that Excel formulas start with an equal sign, put parentheses, and we're going to go 1 plus 1 over this cell here, and then raise it to this cell's power. Hit enter, and then we're going to go over here and do a fill down. And if we click twice on this blue square, it should fill down the values for these values of M. Okay, and surprisingly enough, these numbers don't get extremely large, and they don't go to 0, they don't go to 1. They go to this interesting number that starts off 2.71828. And if we keep adding bigger and bigger numbers to be M, this number is going to slowly start to level off and actually look like something maybe you've seen before. Okay, this is the number E. It starts off 2.71828. So let's go back to our file here. So the answer to the question was, as M gets big, this number here approaches E. We'll say E to the first, and E to the first is equal to 2.718281. I'm going to put ... because this number, like pi, goes on forever, never ends, but has no recognizable pattern. So we could keep writing digits for a long time, but this number, like pi, is extremely important in mathematics, shows up all over the place, as we'll see in the future as we move forward, but maybe showed up for the first time when dealing with these financial calculations. Okay, so if we go back to this formula here, we can replace that inside expression with the number E, and then leave the RT that was up here as the exponent on that base. And so this now is the formula for interest that's compounded every instant. We say that that's interest compounded continuously. It's kind of a theoretical concept because you can't obviously compound things every instant physically, but mathematically we can do it with this formula. And if you look hard enough, you might find a bank or two that actually will do this for you. And this will be the most money you can possibly get from a bank at the same interest rate. So this will give you the most money per year because your money is being compounded every instant, theoretically. So we'll see the number E pop up more and more as the year goes on. The main thing to understand is that E is a number. It's between 2 and 3. It's closer to 3. And it starts off 2.71. That would be good enough, just like pi starts off 3.14. So as you wind up here, these go back to your learning objectives. Make sure you have a good grasp for what these three things we're talking about. And you should be ready for class next time we see you.